Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is walls coloring 2 and it is a hard level problem. So this particular problem says that there is a row of n walls in Geeksland. So basically there are n walls and there are k types of colors, right? And the cost associated with coloring the ith wall with the jth color is represented by this particular matrix, which is called costs, and it is given to us in the input, right? There is one constraint while coloring the walls, that is no two adjacent walls can have the same colors, right? So we just have to tell what is the minimum number or what is the minimum cost which is required to color all the walls such that one single particular constraint is satisfied, and that is no two adjacent walls should have the same color. So let me just show you with an example how this works. For example, this is the test case where n is equals to 4 and k is equals to 3, which means there are 4 walls and there are 3 types of colors, right? Which is represented by the matrix itself. So you see there are 3 columns in every row. That means there are 3 number of colors, right? So this is my matrix and these are the values. So the only constraint is that if I have taken a particular color in some particular row, I cannot take it in the adjacent row. For example, if I take 1 here, I cannot take 5. I can take any of the others. I can take 8, I can take 4, any of those others, but I cannot take 5, right? So so starting from the first row, I can take 1. Then in the next row, I cannot take 5, but I can take 8 and 4. So let me just take 4. Then in the next row, I cannot take 9, but I can take 2 and 3. So I can just take 2. And in the next row, I cannot take 2, but I can take 1 and 4. So I can just take 1 here. So the total cost is 1 plus 4 plus 2 plus 1. That is 4, 5, 6, 7, 8. So the answer would be 8 for this particular test case, right? So this is how the problem works. And I would say that this problem is a pretty standard DP problem. This is just one very slight change to this particular problem. And I'll just start with telling you the DP states. What are the DP states that we are going to maintain here, right? So we will maintain a DP of ij such that this represents the cost of coloring the ith wall with jth color, including all the previous walls. So if I'm talking about DP of ij, it will store the answer of coloring the ith wall with the jth color and also including the cost of coloring all the walls from 0 to I minus 1. So we assume that 0 to I minus 1 has already been computed, and DP of ij will store this particular answer as well as coloring the ith wall specifically with the jth color, right? So our answer would definitely be stored in DP of n, and it can be from 0 to k, right? So when we are at the nth wall, we can take any of these colors. The minimum of these would be our answer, right? So our answer would be stored in this particular state. Now, how do we generalize this particular state I comma j? What will be the answer? So one factor influencing it would definitely be costs of ij, right? And the other factor should be minimum of something, and the minimum of something should be dp of I minus 1 0 to k, right? So I'm just writing it in a pseudo type of form where I'm just trying to explain what it means. This is not the exact code. Since I've written something like 0 to k here, this means that this particular value can have any value from 0 to k, but the only exception in this case is that it should not be equal to j, right? It is the same j that we are using here. Why? Because the question mentions that there is a constraint that no two adjacent walls can be of the same color. So I can take any value from 0 to k here except j, right? This is our constraint. Similarly, while computing the answer, there is no such constraint. So I can take any value from 0 to k here. The minimum of all these values, let me just write minimum also. Minimum of all these values would be my answer, right? So I've explained the DP state that we are going to consider. I've explained where the answer will be stored. So it would definitely be stored in the nth wall and some of the key colors. And I will also explain the normal generalized form of the DP state, how we will compute DP of ij, right? But now there is a big problem that if we try to compute it this way, then DP of ij, obviously I, the number of walls is up to 10 raised to the power 3, number of colors is up to 10 raised to the power 3, and uh, I into j or n into k is less than 10 raised to the power 5. Right, so we can not definitely compute it the answer this way, just because, for example, if you are using one loop for I, one loop for j, it is already 10 raised to the power 5. You cannot take j, or again for k, that is the second part, the colors part, because for example, if you have taken one I 0 n, so this would be for the walls, this would be for the colors. For example, this would be for traversing the ith wall, this would be traversing for the jth color. And for example, if I have formed dp of ij is equals to infinity initially, right? So after it, I will need to consider all the colors in the previous wall and find out their minimum, right? This is what I have to do. So again, I'll have to do for k 0, this is, it is like z0k, and after it I'll have to compute some dp of minimum and minimum of something something, right? So I'll have to use 3 loops here, which is not permissible. I believe that this will definitely give TLE. So what is an efficient solution to this? So instead of computing the minimum of all the values in the previous row, right, instead of doing all of this, what I can do just is I can store what were the values in the previous row itself. So if I just have a copy of the values of the previous row, I can just use their minimum and the second minimum at max to find my answer. Why? I'll explain you why I'm talking about minimum and second minimum. So for example, you are at the ith wall and the jth color, right? So you want to take some color from the I minus, you want to take some value from the I minus 1th wall, right? So it would be something like this. Right, let us say these are the walls. This is the first row which you visited. Then you went to this, and now you are at let's say this particular position. Right. So you would want to take either this, or either this. Right, because we were taking dp of ij is equals to cos of ij plus minimum of dp of I minus 1, and this can be any index, right? The color can be anyone. So you have to take either of these three values. Now, if this is the minimum, you cannot definitely take this. So let me just write case 1 when minimum is same index. Same index. Same index means that the jth color is also used here, and in the previous row also the jth color is used. So what you will have to do is you will have to go to the second minimum, right? It can be either this one or either this one, right? It can be any of those. If both of the values are same, no matter where you go, it's all the same. You can take any of them, right? So in this case, you need the second minimum, or case 2. For example, you didn't want to take this color for this particular row. You wanted to take this color. Case 2, minimum is different index. Obviously, if these two colors are different, you can obviously go from here to here directly. So you can just take the first minimum, right? So instead of going through all the values in the previous row, what we can just do is we can just maintain the minimum two values, right? The minimum two values, and that would do our work, because at max we will just need to go to the second minimum, because there is a constraint that only the column or the color should not be the exact same, right? If it should not be the exact same, you can always bounce back to just second minimum, and that would give you the answer. right? I hope you are understanding what I'm trying to say. If, for example, you were choosing the same color which was chosen in the previous row as the minimum, now you would just have to go to the second minimum, right? That would definitely change. That would either be this or either be this. In both of the cases, you can just come to here. But if the color you have chosen, if the color you have chosen is this one, right? Then you can directly take the first minimum. There is no need of taking the second minimum. So you just have to maintain the minimum two of those. The way I did this was I tried to like simplify my approach without thinking of the minimum and the second minimum. I just used a set of pairs. The reason why I used a set of pairs is because there can be two values of the same value, but I'll use the first one to be the value and the second one to be the index or the color, right? So when I they take these two values, all the values would be distinct in my set, right? So what I just do is I just store all the values for the current row in my set and use it for my next row, right? I'll use this information for my next row. So let me just quickly reiterate what I just said. So we have been given a wall of n colors and n walls and k colors, and we just have to find the minimum cost of coloring all the walls such that no two adjacent walls have the same color. Now I'll form my DP states such as like DP of ij, where the I will be the ith wall and j will be the jth color. So at DP of ij, I'll store the cost of coloring the ith wall with the jth color. Also, I've already computed the answer of coloring the walls from 0 to I minus 1 in DP of ij. Right. So it will store the answer from 0 to I minus 1 plus coloring the ith wall and the jth color with the jth color. Right. So naturally my answer would be at DP of n minus 1, and the index can be anything. I'll have to take the minimum of all the indexes, right? Now when I'm trying to form the general case, how I will compute the DP of ij, it would be equal to cost of ij plus minimum of DP of I minus 1, and the index can be anything. I just have to make sure that it is not equal to j, right? Because I don't want the adjacent wall to be of the same color. Now if I just try to form a simple for loop for all of these values, right, I'll have to make a loop for I, then I'll have to make a loop for j, then I'll have to make a loop for the color of the previous wall. Like, right, I've decided a color j from my current wall, then I'll have to choose a color from the previous wall, right, which has the minimum cost. So I'll again have to run a loop, and running a third loop is not feasible. So what I just do is I just try to maintain a set of minimum elements where I can just directly take the elements. So for example, if I am somewhere around here, if this was the minimum element, right? If I'm at either this, it would naturally make sense to choose the minimum element, right? Because in this case also I was trying to choose the minimum element, right? So it is naturally does make sense to choose the minimum element here. But if I'm at the middle element, then I can definitely not take this particular element because the color of the walls would be the same. So what I instead do is I choose the second minimum element. So it can be either this or either this, it doesn't matter. I just have to take the second minimum element, and the color of the walls does not have to be the same. In both of the cases, if I choose this one or this one, the color of the walls would be definitely different. So there are only two cases. When the indexes of the minimum and the current color that I have chosen is the same, then I have to choose the second minimum. And if the indexes are different, then I can take directly the first minimum. Right? How will I store the information of the minimum? For this particular case, I am using a set of pairs. Now in this particular pair, the first value would be the value itself, and the second value would be the index of the particular color or the color itself, right? So I'm using, if I'm computing this value for the ith row, I'll be using this information in the I plus 1th row, right? So this was all about this question. Now let me just show you the code for this particular question. Now this what I've initially done is I've just initialize my values of n or k because they are not given in the question itself, and so n would be equals to costs of size and k will be equals to costs of 0 dot size. So it can be 0, 1, 2, anything, but 0 would definitely be there, right? So I've initialized my dp array, dp n comma k, and I've initialized my two sets x and y. So why I've initialized my two sets? So x will be having the information of the previous row to be used in the current row, and in the y I'll be having the information of the current row to be used in the next row, right? So when you see the code, you will understand it better. So what I do is I just form my base case for when row is equals to 0 or the 0th wall. So for this particular case, dp of 0i would be definitely equal to cost of 0i because there are no previous walls, right? And I just insert the value of dp of 0i comma I. So this is the actual value and this is the index of that particular value, right? These are the two things I'm inserting into my set. Now I start from the first wall and go up to n. I start from the 0th color and go up to k. So I initially form my dp of ij is equals to 1e9, that is some bigger number considered as infinity, right? Now I just take my pointer at x dot begin. So if this particular pointer is equals to dp of I minus 1 comma j, right? So dp of I minus 1 comma j, this means that it is the same row, right? Or it is the same color wall, right? So if this is same, I just want to increment my pointer. Why would I want to increment my pointer? Because I don't want to take this first minimum. I would definitely jump to my second minimum, right? Now, if this pointer is not equals to x dot n, this means if there were at least two colors, right? Then I would take dp of ij is equals to cos of ij plus the pointer value, and I'm taking the first value because this was the actual value stored in it, right? Now in the y set, I just insert dp of ij comma j, right? So this is the information about my current row. I just copy the, after this all this computation has been done, I just copy my y set into the x1 so that it can be used again for the next row, and I just clear my y set. Now at the end, what I just do is I just initialize my answer with infinity, and for all the values from 0 to k, I go through it dp of n minus 1 because this will be my last wall, and the ith or the kth color, right? So I'm taking the minimum of these. If my minimum answer is equal to infinity, then definitely it means I have not found any answer, so I return -1, otherwise I return the value of the answer. So this is the code for today's problem, walls coloring 2. So you will also find this particular code in the description, so you can check that out also. And if you guys were able to understand the solution, and if you guys were able to derive some value from this video, you can definitely consider dropping a like on this video, and also consider subscribing to the channel, and don't forget to share this with your friends. You can always subscribe to this channel because it is free of cost, and obviously if you don't like the content later, you can always unsubscribe. So till the next video drops, keep coding, stay safe, bye bye.